All right, welcome to day two of the first workshop of the 2025-26 Alaska Sustainable Energy Conference Continuing Conversations Virtual Workshop Series. For those of you who joined us yesterday, thanks for coming back for day two. And for those who are joining for the first time today, welcome. My name is Gwen Holdman. I'm the Chief Scientist, at the Alaska Center for Energy and Power, and I'll be your MC today. As a reminder, this is the first of a series of 4 virtual workshops being held this fall and upcoming spring, leading up to the 2026 Alaska Sustainable Energy Conference. The next dates, we believe, are going to be on October 28th and 29th. And then January and April will be the next 2 quarterly presentations. And these workshops are really designed to take a deeper dive into specific topics that are of current relevance to the energy opportunities and challenges facing Alaska today. Yesterday, we heard from experts in transmission planning who work across the country, discussing transmission planning processes in general, including emerging topics and challenges, and how to go from planning to development and construction. And so our conversation today will include actual hearing from the utilities that we heard about yesterday, starting with the folks from ISO New England about planning practices. And then after the break, we're going to continue on with the presentation by Howard Google from NERC, discussing NERC transmission planning reliability standards. And then at the end today, we're going to hear from Hawaii Electric to hear about planning practices in Hawaii. Before we get started today, there's just a couple of housekeeping items. For those of you that didn't join us yesterday, same things as yesterday. Introduce yourself in the chat. Let us know your name and the organization you're from. If you're having any difficulties with audio or trouble viewing the presentation, please chat event support for assistance. And Monica and Sarah and the amazing team at Government Event Services can help you out. During the workshop, all the attendees are going to be muted. So any questions that you have, please submit them in the chat. And please just go ahead and submit those right when they kind of come to mind. And then we'll go ahead and we'll collect and curate those questions and then use those during the Q&A portion of each section, which will kind of occur after each of the 3 utilities present. The recording of this workshop will be available on the alaskasustainableenergy.com website, along with all of the previous versions of workshops that we have hosted. And so if you do wind up stepping away or you want to rewatch or share a portion of the presentation after the fact, you'll be able to do that. So to start out today, we actually have some remarks from our governor. He was not able to join us today, but was able to record some remarks for this workshop. I know that Governor Dunleavy is very, very interested in these topics and these issues, and he is following these workshops pretty closely.
Thank you for joining us for day 2 of this virtual workshop, which also marks the kickoff of our continuing conversations series in partnerships with the Alaska Center for Energy and Power at the University of Alaska Fairbanks. We're kicking off this series following the 4th and very successful Alaska Sustainable Energy Conference held this past June with speakers and attendees from across the country and around the world. There is a focus on Alaska like never before, as we saw with 3 cabinet members in attendance who didn't just pop in for a short visit. Interior Secretary Doug Burgum, Energy Secretary Chris Wright, EPA Administrator Lee Zeldin spent several days on the ground in Alaska learning about our resource industries and listening to the people who are ready to unleash our energy potential like never before. These quarterly sessions between now and ASEC 2026 will build on this momentum and the ideas sparked at the conference. They will also help us stay focused and connected as we work together toward a more resilient, affordable, and forward-looking energy future for Alaska. My administration's goal is clear: affordable, reliable, and sustainable energy for all Alaskans, and we've been working hard to make that a reality. Last year, I signed House Bill 307 into law, a significant step toward modernizing the rail belt energy system. But that legislation wasn't the finish line, it was the starting point. Transmission is at the heart of this effort. Whether we're integrating more renewables, improving reliability across the rail belt, or enabling new industries and growing communities, our ability to move power efficiently and affordably is essential. If generation is the engine, transmission is the highway, and that highway needs to be expanded and modernized to meet the demands of a rapidly evolving energy landscape. Alaska faces unique challenges, but also real opportunities. I believe we can lead, not follow, when it comes to energy innovation. That's why conversations like today's matter. You'll hear from experts from across the country with deep experience in grid planning, reliability, and regional coordination. Let's learn from them, ask good questions, and consider how these lessons can be applied in a way that fits Alaska's needs and priorities. So thank you again for being part of this and for everything you do to move our state forward. So let's get started.
All right, thank you, Governor Dunleavy. And so I'd like to now turn it over to Felicia Cecilio. She's going to be our moderator for the rest of today. Felicia is the Senior Systems Planner for Golden Valley Electric Association, but she's the perfect person to be the moderator for today for three reasons. First of all, she's a representative on the Systems Studies Subcommittee, which is really where the idea for this workshop originated from. She certainly has the right background to be moderating. She has a master's and a PhD in electrical engineering from Oregon State University. But more interestingly, I think her dissertation was actually on power systems planning methods, which is, very, very close to the topic at hand today. And I've known Felicia for several years. She initially came up to Alaska to work with us at the Alaska Center for Energy and Power, and she's still an adjunct faculty with us today. So she's also responsible for GVEA's transmission planning and interconnection studies and contributes to resource planning and other planning duties. So welcome, Felicia. I'm going to turn it over to you to kick off our program with ISO New England.
Great. Thank you, Gwen, for that very warm welcome. And I say it's time to, let's just get this started. So please help me welcome our first speaker, who's from ISO New England. Her name is Marianne Urban. Marianne is the Director of Planning Services for ISO New England. In her current function, she is responsible for the development of the New England region's long-term load forecast, resource adequacy requirements, and the performance of regional economic studies. And just as a reminder, if you have any questions during Marianne's presentation, please just put them into the chat. We love questions. And then when we get to the joint ISO New England Q&A, I will read those out loud. All right, leave it to you, Marianne.
Thank you very much, Felicia. Welcome, everybody. Thank you for having me here. A pleasure to be here. Okay, so in New England, we have three critical roles. One is to operate the grid. The other is to administer our market. We are administering wholesale markets for the New England region. And then the third role is really our system planning function. So, this presentation is really about our planning process in general. So I know that the focus of the workshop is more on transmission, but I will touch on really all of the aspects of long-term planning in New England. And our regional system planning process is described in the OAT, so our open access transmission tariff. And there's a specific section which is called attachment K, which really contains most of the elements of the planning process. We have other sections of the tariff that deals with specifically the interconnection of generation or load, but any other transmission planning that would be done that is not specific to interconnecting generation or load would be contained in this document. So the activities that we conduct under our regional system plan are summarized in a document that we produce every other year called the Regional System Plan, or RSP. We just published one in 2023, and we're going to publish a new one this year in 2025. So even though it's written in very, very small format here on this slide, the real details of how we perform our transmission planning studies, in particular, for the expansion of the transmission grid in New England, we have two documents that are much more detailed that could be really good references for people in this group. One is our transmission planning process guide, and more importantly, our transmission planning technical guide, which again really describes all of the studies that we do and how they're performed and the assumptions and method that are used to perform them. So again, going back through the high-level picture of our system planning activities in New England, so we It starts with load forecasting and resource adequacy. This is really my area. My team is doing this work. We're forecasting our regional electric demand and energy use. We'll go into the details of what our forecast considers. And then we are looking also at our resource mix. In New England to date, attracting new resources was really done through the administration of a forward capacity market. That's how we were getting our resources. They were really the results of this market. Things have changed a little bit. The states have also been very active in trying to attract new renewable resources. And as you're going to see on a future slide, we're considering some pretty big changes for our capacity market. But so in terms of planning, we're still looking 10 years out, making sure that we're meeting our resource adequacy need and understanding the impact of announced retirements. So that's load forecasting and resource adequacy. And then from there, we also obviously perform transmission planning activities. Again, that's to make sure that we can meet that our load, we can reach the load as we need to. So really making sure we have enough wires to go from the resources to the load. Some parts of the planning are subject to competitive solutions, others are not. As part of this as well, we review, there are some elements of cost allocation that is under our purview, mostly figuring out whether there is any local cost. If a utility is determining that they want to build a certain transmission upgrade with a little higher of a standard, that cost may be localized if it's not just purely needed to serve the load. And then there's new activities under transmission planning also to try to look longer term into the future and be able to better integrate our renewables or any other new resource development that's ongoing. And those are longer term transmission studies. And then the third part of our planning activities, as I mentioned, is really everything that touches interconnection service. So we don't have yet very large loads as many other areas in the US are seeing. So at this point, those activities are mostly generation interconnection focused. At some point, there may be other transmission service, like interconnecting new large load that we may have to handle more regularly as well. So going briefly through the load forecasting, I'm just going to fly through those a little bit because I know I only have 25 minutes. But basically, so the first step really is to produce our long-term forecast. Our long-term forecast and really all the activities in our planning process used to be just 10 years out. We are slowly but surely extending those time frames. So for the first time this year, we have a forecast that goes all the way to 2045. And our regional long-term forecast has four major components. There's a base forecast, and then we are now separately targeting, forecasting the impact of heat pumps adoption throughout the region, the impact of electric vehicle adoption as well. And we have a separate forecast as well. We have a lot of behind-the-meter PV installed on our system at this point. By 2034, we're expecting that we're going to have close to 9,000 megawatt of behind-the-meter PV, so rooftop solar installed on our system. And so we have had, because we don't see this production, it's completely, we're completely blind to it. We've had to really learn to forecast it long-term and short-term also to support our control room. So those are the main components of our forecast. And so they make up our gross and net forecast. In terms of what this looks like, just for a 10-year out today. So in 2024, our summer peak was around 25,000 megawatt. We're getting all the way to close to 28 by the end of the 10-year horizon, with some contribution from EVs. Heat is really just water heating at this point in the summer. And then obviously diminution, the peak is being diminished by the impact of behind-the-meter PV. The very, very large amount of behind-the-meter PV that we've seen is shifting our peak from the mid-afternoon to later at night. So the peak contribution of the PV is actually expected to diminish over time. So that's where we're at in the summer, just to give you a sense of the size of the system in New England. And then in the winter, we're seeing, obviously the big story is that our winter peak is starting to gain more weight and become larger compared to to what it's been in the past. And so we're going to reach a point in the mid to late 2030s where our winter peak is going to surpass our summer peak. And that's really important from a planning standpoint, because all of our planning activities to date have been really focused on understanding everything in the summer. And now we're finding ourselves having to shift to really trying to understand winter conditions and plan the system from a resource standpoint, but also from a transmission standpoint, naturally, for winter conditions. So as well as our peak shifting from summer to winter, we also have now our demand for energy is starting to grow again with the electrification of heat and transportation. So we've seen a net decrease in energy for a while now, for the past 20 years, and now we're forecasting an increase in energy. And then this slide just gives you a sense of the impact of electrification on our peak. So electrification on our summer peak is only predicted to be a small impact. On our winter peak, of course, much larger, and on our total energy demand, pretty large as well. And so to meet this demand and this, the demand is shifting, our use of electricity is shifting, and naturally as well, we've seen a shift in the kind of resources that we've used over time, and that shift is also going to continue. So this slide is really showing what our resource mix was in 2000 to meet our energy. In 2024, you can see that in 2000 we had a pretty balanced mix of technologies. We used nuclear resources, oil, coal, some natural gas, some hydro, some imports, and some renewable resources. In 2024, compared to 2000, the big change, of course, is we were using a lot less oil, a lot less coal. Our natural gas share grew very massively, and then in terms of hydro imports and renewable, we're at about the same place. The 2040 numbers are numbers that are not the results of a forecast or a prediction. They are numbers that were modeled in a study. At the time, we were envisioning a lot more renewable production, but still we would expect the mix towards 2040 to still shift with a lot less gas production and more production from renewable resources. Our queue, as you're going to see on a later slide, is mostly at this point wind and storage. Again, things could continue to shift, but we expect that those means of production are going to take a share there as well. So we have run studies, the economic study team has run studies really far out into 2050. And we've really looked at what it would mean to meet our electrified demand. So with full electrification, trying to meet carbon constraints of as little CO2 production as we can possibly get to, and using mostly wind, solar, and storage to get there. And what we've uncovered, which is not really news, but I think worth saying, is if we want to get a full decarbonized mix by 2050 while meeting the electrification objectives of our states, and only relying on adding wind, solar, and storage, this will require us to make very significant additions to our installed capacity. So very large numbers. This is average per year. It's not exactly how things would develop over time, but if you average the development over the next 25 years, you're going to quickly see that the numbers are really large. And then naturally the story between the, again, change in demand, change in the resources that are being used to meet this demand. It's also a classic story here that we see in the US is we're now starting to see a lot of retirement of our older fossil fuel-based generation. And a lot of those resources are pretty old. And so we have here a map of the generation that has retired already. So we've lost some nuclear resources, oil or coal-fired steam units, and then we're expecting there's a few more units in the system that are also at risk. So we're just making sure to manage our resources and our demands, noting the risk of additional retirements. And then, as I mentioned, the way that we attract resources in New England is really driven by our capacity market. This is a primary tool used to attract resources. New resources. And so we're going through some significant reform with the market. We used to have a forward annual market. As you see now, there is really a question of being able to, so that forward market was really giving us the resource mix we needed to meet our summer peak. But as we're shifting slowly to from a summer peak to a winter peak, that market needs to change. So we're moving from an annual to a seasonal market. And then we had a we had a forward design that was really based on assuming that the type of new resources that were going to come were combined cycle gas turbine. That was really the resource of that we were expecting to see. It was the most economic to come and join the fleet. And that has changed over time. And so the 3 to 4 year ahead period is not working as well as it used to. So we are shifting from a forward market to a prompt market. So we are in the process of designing the new market, and so we're not going to be implementing it until 2028. And so if you want to learn a lot, there's a lot of materials out there on our website. So now moving on to maybe the part, so we've covered the demands, the resources, the part that is maybe of most interest to the folks on the workshop, transmission planning. So we have 9,000 miles of high voltage transmission line, 13 transmission interconnection with New York and Eastern Canada. As you've seen on the prior slides, we do meet some of our energy needs through imports. So the interconnections with our neighbors are good for us. And we have in New England invested already quite a bit of money in upgrading our transmission system. So since 2002, we've already invested $13 billion of in just transmission upgrades to meet our load and make sure that we also met all of the standards and criteria that we needed to meet from a transmission planning standpoint. There are more projects that are planned, about 447 million. And then we're also having developers separately that are proposing large transmission projects that will connect us to our neighbors to the north. There is a later slide on that. So in our regional transmission planning process, there is 3 main types of projects. There is actually 4 now, but so 3 that we're really focused on a 10-year plan, and then a 4th one that we just introduced a couple of years ago. So we have reliability projects that are here to maintain our ability to deliver power, considering really load growth. This is load serving upgrades and considering generator retirement. So again, with the generator retirement that we have in the pipeline, how can we serve our load serving upgrades? Then we have system efficiency projects. The goal of those projects are to reduce congestion. So if we have a pocket where we have a lot of renewable generation, let's say, and there are a lot of congestion on the system, and that really increases the production cost of our system, then we have a process to put in place system efficiency upgrades, transmission upgrades that could maybe unbottle that generation, for instance. So they would not be necessary to serve our load, but they would make our system overall more efficient from a again, production cost standpoint mostly. We have other criteria that come into measuring system efficiency, but it's the idea. We want to reduce congestion mostly. Then we have public policy projects. I'm going to skip over that category a little bit because those were meant, again, to help satisfy the public policy desires of our states, but we really haven't implemented any public policy projects. So that it's not really a part of the tariff that we've used or that is being that has led to any transmission upgrades. And so instead, I'm going to be really focusing on the next page, which is much more active, which is a longer term transmission studies, and they serve a similar purpose. So this was actually a state requested process. They really wanted us to identify transmission upgrades, again, that would help them meet their objectives. So we did, and there were also upgrades that would be looking at a longer time frame. So we did a first longer term transmission study called the 2050 transmission study that was completed in 2024. And out of this, that transmission study highlighted the kind of upgrades that would make the integration of the kind of resources that the state were interested in easier. So out of that study, we are actually in the process. We just launched the first RFP, and the kind of upgrade that we're asking to build are upgrades that will allow us to increase our transfer capability in Maine, for instance, and also interconnect another 1,200 megawatt of wind resources in Maine. So those are, again, the type of upgrades. They're not load serving. They're not upgrades that will reduce congestion, but they are upgrades that will help ease the integration of resources and the state's ability to meet their long-term goals in terms of the kind of resource mix that they would like to see on the system. Overall, the transmission planning process, obviously, the goal is to ensure reliable, timely, efficient, and cost-effective transmission solutions for New England. We obviously have to also we have to take into account our stakeholders' expectations, but also make sure that we respect all regulatory requirements. And to be reliable, the transmission system must obviously ensure that all of the equipment that we use is operating within its limits. So thermal capability, voltage capability, short circuit capability. We also want to make sure that the generators remain stable, that inverter-based resources remain online for design contingencies, and Brad's going to have more on those sorts of issues. And then that we don't create widespread generator outages or load interruptions for specified contingencies. The interesting thing I wanted to point out, again, I'm not responsible directly for transmission planning, but I've worked with Brent Oberlin, who is in our team long enough to know it's actually more complicated than it looks. There are a number of planning standards and criteria that we have to respect. So NERC, NPCC, and of course, our own planning procedure. And what's interesting is they apply to slightly different chunks of the system. So NERC is generally going to apply to facilities that are greater than 100 kV. NPCC is going to apply to anything that's designed that's determined to be bulk power system. So there is actually an analysis that's being done under A10 to figure out what elements of our system fall into the BPS category. And then we have our own ISO New England pool transmission facilities. They are usually non-radial facilities that help transport the bulk power through New England. But funnily enough, and I'm going to go through the next slides very quickly to get to the next table. They don't all fall neatly in one category or another. So, I confirmed with my colleague that actually we have pieces of the systems that fall in each of those categories. So it's a bit of it's not easy for the transmission planners to make sure that they really follow all of the NERC and PCC and ISO standards for all the right pieces, the right chunks of the system. I mean, most of the system elements are going to fall in category 4 and 5, but again, in each we have elements that are going to fall in each of those categories. So something to think about as standards and requirements are considered in other parts of the country. This is a complexity that we don't really enjoy dealing with. And then, so again, we have the load or resource mix. We have a process to create transmission upgrades that help serve the load, or that helps make the system more efficient, or that help integrate the kind of upgrade that the states would want to see to meet their decarbonization goals. And then the third piece of the planning process is really the interconnection service, managing the interconnection service. So there too, there are some big changes going on. We used to have a queue, and it was really a first come, first serve way of managing the queue. So a generator project would secure a place in our queue, and then we would study generator in queue order. There's been queue backlogs all over the country. It's been talked a lot everywhere. The queue has just become so large. It's become very, very hard to manage in a sequential order. And so there was an order issued by FERC back in July of 2023, order number 2023. We filed our compliance with that order. And the major enhancements is we're going to shift from a queue that's first come, first serve to first ready, first serve. And we're also shifting from a queue to a cluster process. So we're going to study a bunch of projects together instead of studying them one at a time. There are additional penalty structure to make sure that us moving through the cluster process and the interconnection process is timely enough, both for the ISO and the transmission owners. And there are increased financial and site control requirements for the developers. So we make sure that we have real projects, that are well formulated in the developers' heads before they go through the interconnection process. So again, at a really high level, there's an interconnection request that gives us a lot of information. It's not so basic. There's actually quite a bit of technical data that's needed. And again, I think this is an area that Brad's going to touch on. There is more and more technical data that's needed because the studies are getting more and more complex. Then we perform the cluster study. We determine the exact list of upgrades that will be required for all of the interconnection requests that fall in that cluster. And then out of this, there will be 3 parties agreements between the generator, the ISO, and the transmission owner. And those interconnection agreement also details the kind of upgrades that are expected to allow the interconnection of the generator. And then at the end of the process, the construction will begin once the interconnection piece is finalized. So just to give you a high level of our queue, again, this is a comparison between a before and an after. Back in 2017, we still had a lot of natural gas entering the queue and quite a bit of wind. And this is now the state of our queue in 2025. And you can see why there was a lot of work towards queue management and why we had the third quarter 2023. You can see the size of the queues really increasing. We had 13,000 megawatt in 2017. And we now had 37,000 megawatt of, again, project waiting to be interconnected to manage in 2025. So, and in the wind, so it's a combination of offshore wind and onshore wind, mostly offshore wind, but there is also onshore wind in there. So next I go to what it all becomes, what becomes of all of this. So all of those transmission upgrades, whether again they're load serving or system efficiency or long-term upgrades or interconnection upgrades, they end up in our regional system plan project list. So I'm going to show you a screenshot of that list, but all of those upgrades are listed in there. So upgrades from the transmission planning process, upgrades from the interconnection process. We revisit the list, we revise it 3 times a year. And then we have an open stakeholder setup called the PAC, the Planning Advisory Committee, where all things related to our planning process are discussed. And then the final version is posted on our website. So this is a screenshot of the project list. So you can see the project there, the description of the project, and then obviously the in-service date, and then the status of where the project is at. So we have several categories: proposed, plan, under construction, in service. And so we have a status here. And again, all of that information is updated regularly. And then an estimate of the cost as well. So the transmission cost allocation is another sticky point and something to think through. So in New England, at a really high level, it's more complicated than that, of course, when we get into the details. But reliability, so load serving and system efficiency upgrades, they are allocated based on the load share. So it's really measured based on the average monthly peak load. And so whatever your share of the average monthly peak load for the region is, this is the share of the upgrades that you will have to pay for. Public policy transmission upgrade, those were allocated slightly differently, but again, we really haven't implemented those. So I'm not going to spend a lot of time on those. And then the last type of upgrade in the transmission planning process is this new process we put in place, the longer term transmission upgrades. And just to show you, so for those upgrades, if they have a benefit to cost ratio that's greater than 1, it's pretty much the same allocation as for reliability or system efficiency upgrade. But if the BCR is less than 1, the process is such that we may still go ahead with the upgrades, but then a portion is going to be allocated, socialized across the state proportionally to the load, but then a portion is going to be assigned to some specific state. So cost allocation can become very, very tricky. And then just to emphasize, most of the transmission that's going to be built is going to be as a result of our planning process, but developers can also choose to build transmission. There is a process called elective transmission upgrade, where a developer may bring a transmission project forward. In this case, they would pay for it. It would not be socialized through the system. We would conduct a system impact study, and then the project would be funded entirely by the developer. So there is also a process. If someone wants to come and build a new transmission line, they can do that. And those kinds of elective transmission upgrades, they would be used, for example, to bring hydropower from Canada or to interconnect offshore wind or onshore wind. So there are instances where we see them, and we have about, I think about 9,000 megawatt of such projects in our queue. That seems a little high, but we have seen those elective transmission upgrades being brought through our queue, and some of them are being built. So that's it for a nice overview of our system planning process in New England.
Fantastic. And thank you so much, Marianne, for that great presentation. Oh, so you're transitioning from a summer peak to a winter peak? And what we're seeing in the railroad is actually transitioning from, like, almost always have been a winter peak, and now we're seeing higher and higher summer loads. So it's somewhat the opposite. And I was just wondering if there's lessons learned from your guys' transition from summer to winter peaking that would be perhaps tips for us as we transition almost in the other direction.
Yes, it's a big change really that we see and that we're struggling with a little bit. I shouldn't say we're struggling with, but we're working through is the summer peak. It was really focused on meeting the peak hour. It's almost, to us, certainly a simpler problem. It's just having enough resources to meet that peak hour. Whereas the winter peak, it seems to be really correlated to more of an energy issue. It's not enough to be able to serve the peak demand is one thing, but your demand is also related to how much fuel do you have stored in the tank, or how much energy do you have stored, or how much energy you can access from your neighbor. So it becomes sort of this blend between really managing the peak hour, but also managing the demand over a certain duration and making sure you don't run out of energy altogether. So whether it's, again, as stored fuel or just as storage.
Well, we have another question for you, Marianne. And this one's from Steve Colt. How is the high-level resource adequacy requirement determined? Is there any allowance for trading off resource adequacy versus cost?
Yep. So we have a requirement. There's a standard for us that we need to respect in terms of resource adequacy. So the way it's done is we calculate our requirement, and our requirement, we have to have enough installed capacity. So that's, again, under the old world, it's still the case. So we have to have enough installed capacity to have a loss of load expectation that is not greater than 0.1 day per year. So that's a requirement that we have to meet. And based on that requirement, we determine exactly how much installed capacity we need. And then based on that point, we develop a demand curve. So there is a demand curve that's being fed into our capacity market. And then we clear based on that demand curve. So I would say that resource adequacy versus cost is managed through the market clearing. So we could, the market clearing ensures that if we're going to start to look short, the prices of the capacity is going to shoot up. And so there will be more incentive to bring up capacity. If we start to be long, then the price of capacity is a little bit lower than, again, that anchor point of just being right at 0.1 day per year. So that's how we're managing the trading between the two.
So now we're going to stay with ISO New England, but jump topics, and we're going to go over to Brad Marzakowski. So Brad is the supervisor of the Resource Integration Group at ISO New England. His team manages dynamic models, reviews validation reports, develops regional requirements for interconnections, and leads EMT-related activities. And he has a presentation today to discuss electromagnetic transient, or EMT for short, modeling practices. And we will get to questions after Brad's presentation for both the ISO New England presentations. All right, Brad, you can take it away.
All right. So, hi, everybody. I'm Brian Moroskowski. I'm the supervisor of resource integration here at ISO New England. And my team, we deal with all the dynamic models, EMT models. We run studies for dynamic control changes. We do interconnection studies for non-FERC jurisdictional interconnections. And we also implement a lot of the standards that come through for reliability from the NERC, or voluntary standards like IEEE or SIGRI standards. So today I'm going to be talking about EMT models and EMT studies and methodologies. And so kind of the first thing here is, so when should you run an EMT study, right? When should you perform an EMT study? And so the answer there is, for us, we run an EMT study for any interconnection request coming in. We will, run them specifically for power electronic switching type resources, so inverter-based resources, StatComs, batteries, VSC, HVDC, anything that has fast switching that can't really be captured in PSSE or positive sequence space. Other times that we will run these studies outside of interconnection space is, our operations group has recently started taking up some of these studies as well. And again, we're looking for things like weak system conditions, subsynchronous oscillations, control interactions, and general, ride through. The idea here is that the EMT models do have a higher fidelity than the positive sequence models. And so, that phenomena can be really important to understand, as more and more of these sorts of sources come onto the grid. So, how ISO New England generally will, kind of set up these studies, right, is, an interconnection request will come in seeking to interconnect to a specific area, say a substation. And what we'll do is we'll look at that kind of substation and we will build out a sort of boundary, right, a case around that specific interconnection point. Now, we use Manitoba HVDC's PSCAD software in conjunction with Electronics' eTrans software to do this. We'll start with actually a PSSE case, which is positive sequence modeling, and we'll convert that into a EMT case or a PSCAD case. And the reason we do that is because we already have a lot of infrastructure set up around building the models and the cases in positive sequence space. And so it doesn't really make sense to re-accomplish all that effort when you get into EMT space. And so we do port that over. There are certain caveats there, right, that you have to be mindful of when you're doing that. It's not always simple enough to bring a transmission line over and model it as either a pi model or a Bergeron line model. Sometimes, if it's really local to your specific study, you may want to use a frequency dependent line model or what's called a distributed parameter model. And that'll give you a much higher accuracy, right, for the actual phenomena on the system, as opposed to a more averaged response. So we'll take all that information, we'll put it into our cases like that. We'll do that sort of translation. We'll replace the models that are specific to the study. So we'll generally use the generic sort of PSCAD implementations for synchronous generation. But when it comes to inverter-based resources, we will use the specific OEM models. And those are required to be submitted, which I'll talk a bit about model submission requirements later, but those are required to be submitted as part of the interconnection request. So, now that we have our kind of case built, right, we know what we're studying, what we're looking for, where the project is interconnecting, we will start to, scope out what we're going to actually run in the study, right? And so ISO New England actually does apply all of our same requirements that we have in our technical planning guide. As Marianne was pointing out, we have a lot of different standards, different NERC standards that we have to meet in transmission planning space, and we will actually apply a lot of those same criteria into EMT space. So, as required under the FAC 02 standards, right, ISO New England's required to do these sort of interconnection studies. And we list out also that these EMT studies are required under our schedules 22, 23, and 25 under our open access transmission tariff. The specific implementation of these studies, again, mirrors the normal sort of dynamic study or stability studies that are required of those NERC standards and FERC pro forma. But again, we just merge in the EMT side of it because EMT is considered a type of dynamics. And so that's sort of why we are running the same sorts of studies and analysis in EMT space. And that's again specifically because in positive sequence space, when you run those, there are certain phenomena that even though you run the same disturbance, you won't actually see those quantities in the positive sequence space as opposed to if you run it in EMT space, assuming that your EMT models are equipped and of high enough fidelity to actually show you those sort of phenomena. So interconnection, system impact studies do require full N-1, N-1, fault testing, along, as I mentioned, with any other EMT analyses identified during the scope, and these are decided on using engineering judgment. As I mentioned, we set up these sort of boundaries. We cut out a portion of the system because it's very difficult to run an extreme, a very large part of the system, and so we will actually as I mentioned, cut out certain portions, and we'll develop a boundary of equivalencing the outside network in order to be able to capture the, again, phenomena that we are looking for, but also to make sure that we can run it in a reasonable amount of time, right? EMT studies are notoriously computationally expensive, and so it's very important to understand how large of a system that you're trying to model and run here. And that's why in pretty much every case, we're running these studies using parallel processing. So now getting into a little bit about the EMT model requirements. We have a full set of EMT model requirements listed in our Planning Procedure 5-6, which again is pointed to, for compliance with interconnection studies via our, open access transmission tariff. So all these requirements are, kind of upfront and right at the beginning of the whole process for an interconnection request. So these, the models are required to be provided to us in the format that we, tell them to. So pretty much as of right now, we're saying we want these models to come in under Intel Virtual Fortran compiler 19 or higher. We're saying that they have to be PSCAT 5 compatible. We have a whole checklist of different requirements for these models. And we also have, specific testing and benchmarking that's required of these models as well. And then afterwards, we also do a bit of playback testing with these models now, which is a fairly newer thing that we've been doing. But again, it's to really check on the accuracy and validity of these models. And sorry, these diagrams here are just kind of to show a little example of what we require for these submissions. We do like to see these models come in as components rather than a big mess of different smaller library components of PSCAD. One of the requirements actually in the checklist here is that the models come in using real code. And so what we mean there is that the actual code that goes into the hardware in the field is also required to be the same code that's in the models. And again, that's how we get towards, having this accurate model, which the NERC has pointed out in many disturbance reports as being sort of the one of the culprits for the different disturbances that we've seen across the country. So another big item here is that the models must represent the full detailed intercontrol loops and power electronics of the device. Again, we're applying this specifically to power electronically switched devices, and so we are looking for those to be explicitly modeled and not an average source. In some cases, we do have to accept an average source model. But otherwise, we want to see the full the full representation of these control loops and the electronics that they're controlling. That way, we're not missing any any issues in the switching that could end up resulting in a trip of a resource or reduction of output of a resource. And so we can point to real world examples of why this is important as well, which I'll talk about a little bit later as well. But the Iberian Peninsular blackout is a perfect example of a lot of inverter-based resources being on a system, without full understanding of their phenomena that they're injecting onto the system. So another part we ensure the accuracy of these models is we request these EMT model attestation forms, and these are a requirement again as part of that interconnection request. So again, we're front loading all of these requirements to even get into our new cluster process, right? So the interconnection request comes in, has to provide these models, has to provide these attestation forms for the models, has to provide the model quality testing, model benchmarking, and so we're really putting a lot of this emphasis up front on the models to again make sure that they're accurate and make sure that they're going to be useful or easily used in the studies. That way we don't run into a scenario where we're trying to debug model issues during the study time frame. Because as Marion pointed out, we have moved to the FERC Order 2023 implementation of cluster studies, and so those come with certain deadlines for the studies, and so and that are backed by financial penalties, and so we don't we don't have a tolerance for that. So these requirements are meant again to get us to a point where we are not having an issue. But in general, what these attestation forms are asking for is a bunch of information about the OEM and the equipment, and making sure that the OEM and the developer are in fact working together on these models and have provided them after working with one another. So the next part here, once we get the models in through the interconnection request, we have the attestations, everything's signed, right? We've reviewed those materials coming in. We then will run these through model acceptance testing for the for these inverter-based resources, and these tests are designed to make sure or evaluate again the efficiency, the usability, and the accuracy of the models. We generally assume that the EMT models are going to be the most accurate or sort of the ground truth of the models, or sorry, of the resource. And so we again, we put it through these sort of tests. This is run on a SMIB setup, which is a single machine infinite bus setup. That way we can really test just the model itself rather than how it interacts with the rest of the system, because that's more for integration testing and for the study to sort of bear out there. Another part of this here is to benchmark it with the PSSE models. So something, a challenge that we ran into before was that we were noticing pretty significant differences in how a positive sequence PSSE model would work, respond to a certain disturbance versus how the EMT model and PSCAD would respond. And so in many cases, what we found was that the PSCAD model, the EMT model, was accurate, and the PSSE model was actually not accurate because it was more of a generic representation, or it's parameterized generically. And so now we have this benchmarking requirement to say, benchmark these two and make sure that they are, reckoning the same, while also making sure that the EMT model is the best and most accurate representation of the field equipment. And so you can kind of see how if we validate, or the PSSE model against the PSCAD model, and the PSCAD model has been vetted by the OEM, then we end up with both accurate PSSE and accurate PSCAD models for positive sequence domain and time domain simulations. Let's see. I think that's everything there. So this is generally our PSCAD model management process. So we've been talking about everything in this sort of interconnection review portion. And where the project submits their model to us, it goes through interconnection request review. That project model then goes to one of our consultants, who we use to run these studies. That then after the system impact study is completed, though, that as studied model comes into our model repackaging. So another thing to keep in mind with these EMT models is they're not always easy to use. So it may be accurate, it may work, but it doesn't mean that it's very efficient to use. And so we actually have certain requirements now around the usability of the models as well, to make sure things like reference signals are easily accessible by the user. And to make sure that certain flags and quantities are able to be measured and reported by the model. And so that's kind of the purpose of this model transfer section. So after the study is done, we've showed that there's no adverse impact on the system from the project, but then we want to take that model and get it into our library so it's ready to use for the next study, right? So for the next study, we want to make sure we have this library of existing models for each of the resources that are going to be, again, within that boundary that we decide that we're going to study. And so that's where this model packaging comes in. After that, it becomes what we call our reference model, which is, again, our sort of base truth. And you can also see that we have model update and maintenance process flow as well. And in that portion, we are receiving updates to these models from the developer through our market registration process. We have certain requirements for them to provide us with updates to their models. So if they change their inverters, if they make parameterization changes, if impedances for the gen ties change, right? Those are the kind of things that can come in, and then we'll actually update the models. And that will then become the new reference model. The last section here is more the EMTWG substitution library build out. What that's referencing is where we actually take this reference model, and now we break it out into a parallelized version, and to make it more plug and play. So again, these EMT models generally are not plug and play. They're actually generally pretty difficult to get initialized and running in your studies. And so the aim of this process is to take those models and reformat them, not changing the performance of the models at all, or their responses to disturbances, but to sort of package them up in a way that any engineer can just pick it up, plug it into their case, and run with it. They don't have to worry about initialization. They don't have to worry about their run times. They don't have to worry about their step times, right? All of that stuff is already predefined and set up for them, so they can just grab their model and go. A big part of EMT studies is the case setup. That's one of the largest time constraints and manpower constraints. And so if you can solve for that as well alongside the computational constraints, then you can get these EMT studies done much, much quicker. So here's where I was talking about the kind of examples of verification and validation. This is an example of our benchmarking. So on the left, you see some results from PSCAD testing. We can see, there's the active, the power here does not really match the green trace on the right here. And the megavars here, right, you have the spike, but there's a bit of a drop. And so, just in generally, it's not matching. You also see oscillations in the PSCAD model as we're in PSSE. Everything is just flat, and you don't really see any of this. And this, again, is, kind of getting to where there's control interactions, right, and oscillations, high frequency oscillations that you can see in EMT space, which can happen on the real system, but you would never see them if you were only running a PSC or positive sequence simulation. And so here in this example, afterwards, there were mitigations. So this actually turned out to be a real world issue where those oscillations were present in the impact study, and so mitigations were developed in order to not only correct the model accuracy, but also to correct for those oscillations. Here, the fix was to actually add a synchronous condenser to behind the POI of the resource. And so what we can see here is that now that we have these oscillations that's coming from the synchronous condenser, and so the idea here isn't to get a 100% one-for-one match, because you're not going to get a one-for-one match between PSCAD and PSSE. And that's just because they're different domains, right? And PSCAD is generally a higher fidelity model than in PSSE. But what you're looking for is that PSSE, remember, is an averaged model, right? It's an approximate averaged model of the real performance of the system, as where PSSE is meant to be a more aligned representation of the actual system. And so as long as your averaged performance is aligned with the PSCAD performance, then that's what we consider a good benchmark, right? That we would consider this acceptable. So more on the real world example here, and again, why we think EMT studies are very important for reliability of the system. This is an example of an actual disturbance that happened on our system up in Maine. There was a breaker that had low SF6, and it opened just unexpectedly. And this resource, this was a solar plant, reduced its output by roughly 80%. And that was very unexpected, because when we go back to the models and we play back the same sort of voltage and angle, into the models, we didn't see that performance, right? And so even though it got through all the way through the interconnection studies and got through all of our vetting, because again, this was not a sort of contingency or disturbance that we normally would look at. The model did not respond in the way that it actually did in the field. And so, since then we have implemented the attestations, and we've taken a few more steps to ensure the accuracy of the models. But again, this is why it's so important, and again, this is why I point to the NERC disturbance reports, the Iberian Peninsular blackout reports, because in many, pretty much all of these disturbances, what the planners saw and what the operators saw in their studies was not what actually happened on the grid. And it's traceable back to these models not reflecting this behavior. And so, since since this disturbance happened, we have since followed up with the owner to make corrections to that model. So there is a feedback process there. So kind of wrapping up here, some lessons learned here is that EMT studies are much more time intensive than traditional transient stability studies, given that they are far more complicated and computationally expensive. As where you can probably run a stability study is if you have your models, set up, you can probably put one together in, a few weeks, maybe a couple of months, depending on what you're seeing. That same, study may take anywhere from 6 to 9 months, in EMT space. Like that's how much longer it is, right? You can run a 20-minute, a 20-second stability simulation in probably 10-20 minutes on a normal laptop, but if you try to run that same disturbance with a large part of the system on that same computer, it's going to take 12 to 24 hours to run that one simulation, depending on your time step. So things that you need to look at now, as you start to get from somebody who's just starting EMT and starting to get into it, the main things to look at are making sure you have the resources, right, the manpower to apply to it. Make sure you have the hardware resources to apply to it, and the expertise to apply to it as well. Again, given that it is far more complicated. But in the end, EMT studies can show things again that are most likely missed in your normal stability studies, and that's specifically because where you would want to use the EMT studies for inverter-based resources. Also, starting early and doing these sort of studies in parallel is also going to save some time on those studies. And I already mentioned hardware. So some future work for the ISO that we are doing is, I kind of hit on this a little bit. We're developing our EMT model repository to have this sort of single source for up-to-date EMT models that are plug and play. And then we're also investigating hardware setups. So between like having a dedicated resource in-house, or if we farm it all out to the cloud. So we are looking kind of what is the most beneficial, what's the most economic for the ISO's purposes. We are looking at designing automated testing and verification tools for EMT models. I sort of mentioned the model acceptance testing, but as we move into the future, we're also adopting IEEE 2800. And so we will be using those EMT models for IEEE 2800 conformity assessments as well. And then kind of a subject of research for us is the viability of hybrid simulations, where you're actually having PSCAD and PSSE kind of talk to one another. So that's everything I had, and I think I did add a primer, sort of for folks who are just starting with EMT at the end here. Hopefully, some folks find that useful. But I think I've used my time here, so we can probably jump into questions.
Awesome. Thank you so much, Brad. I think we're going to do one or two questions here. So I'm going to pull the first one for you. This one's from Dave Burlingame. Do you model and study all IBR interconnections with EMT, or only those in parts of the system with low system strength? And then what is the process of a new IBR facility? If a new IBR facility appears stable in the studies, but an adjacent one appears unstable. So two parts there.
Okay. So sorry, could you say the first part again?
Yes,
Or
we'll just
is
stick
it
with the
in the
first part
chat here? Okay.
Yeah. Do you model and study all IBR interconnections with
Okay.
EMT, or only those in parts of the system with low system strength?
Okay, so we do model and study all IBRs coming onto the system, regardless of where they're coming on the system. Um, that and that's because yeah, we generally have other things that they may interact with, regardless of where they're on our system. Yeah, we've found low system strength conditions in some of what we've previously thought were the strongest parts of our systems, and so it's yeah, and so that's why we run it everywhere, regardless of where the where the IBR is interconnecting. And the process of a new IBR facility appears stable in the studies, but an adjacent one appears unstable. Um, what we'll do is we will look at both of them. We'll look at them independently, and then we'll look at both of them together. In the new cluster study process, I think they would actually end up both being held responsible to make sure the system was stable and develop mitigations for that. Previously, though, in the serial process, we would have tagged one with an upgrade and not the other, because one would have priority, for example.
Thank you. And then we'll do one more. This one's from Dan McIntosh. How are you handling model verification of EMT model parameters by the OEM in the field?
Handling model verification of the EMT model parameters. So we do not ask them to verify specific model parameters. The point of the attestation is to make sure that the OEM has signed off on the parameterization of that model. So if there is a difference in what's in the model versus what's in the field, then the OEM is really on the hook there, because they've signed an attestation along with the generator owner having signed an attestation to say that it is parameterized correctly to represent the in-service equipment of the physical facility.
Gotcha. Great. Well, thank you so much. Well, welcome back from the break, everyone. To continue with our program, please help me welcome Howard Google from the North American Electric Reliability Corporation, also known as NERC. Howard Google is the Senior Vice President of Regulatory Oversight at NERC. In this role, he is responsible for directing programs and processes to monitor, review, and evaluate program effectiveness of the Electric Reliability Organization, or ERO's, enterprise's implementation of risk-based compliance monitoring and enforcement. Welcome, Howard. I'll let you take it away from here.
Thanks, Felicia, and good morning, everybody. Thanks for having me here. So very happy to come and talk with you. Going to speak a little bit as to what we at the ERO do, what NERC does, and then talk a little bit about how we do our standards process and all of the stakeholder processes. And then again, at the end, talk a little bit about what our transmission planning standards are. You're familiar, I think, with our TL standard, but we have some other standards that actually apply to transmission planners too, and we'll kind of step through that just to give you an idea on that. Also thought it might be helpful to know a little bit about our history. NERC has actually been around since the first Northeast blackout that we had back in 1965. Following that, it was determined that we needed to work together as basically the 48 states, and so we developed the National Electric Reliability Council. Within a couple of years of that, we began to develop much more stronger ties with Canada, specifically Ontario and Quebec, but some of the other provinces too. And so it was determined at that point to change the name to North American Electric Reliability Council to more accurately reflect that. At that point, it was more of a voluntary organization. Utilities all across North America got together, developed kind of rules of thumb and agreements for how we would operate the system, both from a planning perspective, from an operating perspective. And that worked for many years. And toward the end of the 90s, it was determined that we'd start developing some standards that would be voluntary standards at that point, but something that everybody would agree to. And so late 90s, early 2000s, we began to change all of our operating policies and planning policies and procedures over into standards. And then in 2003, as you're all aware, we had the Northeast blackout again. Congress stepped in, did some look at it, and said, we really need something other than voluntary to go on here. That may work okay for a while, but it seems like we really need to make something mandatory and enforceable. So they came up with this idea called the Electric Reliability Organization and said, we really need to have somebody that can develop mandatory and enforceable standards and then also go out and enforce them with monetary penalties and other penalties. And NERC at that point was chosen as the ERO. To signify that, we changed our name, basically changed council to corporation, and that way we could keep all the logos and the coffee mugs the same with NERC, but go ahead and signify that we had done something different. We at that point also developed memorandums of understanding with the various provinces that we'd had agreements with in the past too, to also operate as the ERO for them in addition. And so in 2007, we were basically provided that ability to be the ERO and work throughout. It is interesting. I do mention this as a little trivia fact. We actually had our standards become mandatory and enforceable in Ontario prior to the blackout. So they had already taken the step to do that in Canada. So we always make a point of saying that they were on the cutting edge of starting to do that, but it was certainly recognized after the blackout that we needed to take some steps in those areas. So as the ERO, we're authorized again to develop standards, to monitor compliance with those standards, and to issue any sort of penalties that would be necessary for that. You also have some additional qualifications there. We do near-term and long-term assessments of the North American grid, at least the 48 in the provinces that we're connected to, and publish those. So we do a summer assessment, a winter assessment, and then we do a long-term reliability assessment, which looks at a 10-year out window to determine resource adequacy and any issues that we would see on the system there. We also are somewhat unique in that we have a program that certifies operators as having the ability to do their job. They have to go through training and go through recertification, and we require certain positions in North America to be manned by those, especially for our reliability coordinators and our transmission operators and balancing authorities, those three. And then finally, we also maintain situational awareness across North America by having some interconnections with all the reliability coordinators. So they send data across the reliability coordinator information system. We have a terminal off of that helps us look at that too, so that we can at any point be able to determine how the system is operating and be able to provide that information to any applicable authorities that might have questions on it. One of the ways that we operate, and you'll hear me talk about the ERO and the ERO enterprise. Technically, NERC is the ERO, but we also operate through our regions throughout North America. So we have 6 regions that we delegate some authorities to. They're the ones that actually go out and do the audits. So they interact with all of the specific entities, and they have the authority to do that. They also collect some data that we use for our assessments, and they're kind of the boots on the ground to help us understand for situational awareness and events analysis what's going on the system. You can see the names of those here. 2 of them, one of them is the Texas RE, which is the most of the state of Texas. Everything west of the Rockies is in WEC. And then we've got the Eastern Interconnection, which is the vast majority of the other 4, with the exception of Quebec. Quebec is its own interconnection too. So we've got, we joke that Quebec and Texas have a lot in common because they both want to be their own interconnection. But each one of those operate independently and are tied with DC ties. As we are transitioning from the traditional generation and traditional transmission system that we have, we also think that there's some pillars that we need to take into account for establishing the way to progress forward. We feel that we need to progress to a low or a no carbon energy resource plan, and we want to make sure that we've got sufficient amounts of that energy to achieve the decarbonization goals. That has kind of opened our eyes to the difference between the way we used to look at capacity and the way we need to look at energy today. It used to be a very simple exercise to determine, whether or not you had adequate capacity to get through summer or winter. You just sum up all the generation that was installed. You'd look at what the load projection was. Generation was greater than load. You had a thumbs up. Everything was good. But now we have resources that are variably dependent. So solar is very dependent on the amount of sun that you have and the number of hours that you have for that. Wind is also very dependent upon, wind generation. And then when you talk about batteries, you have to understand that a battery is not a generator. It's really a time shifting device. So you have to charge that battery at some point if you want to draw that energy down from it later. So those types of calculations need to go into that broad calculation about whether or not you're adequate to go through a summer or a winter season, as opposed to, again, what we did traditionally, which was just summing up the amount of capacity that was installed. We also know that that's going to also require new transmission resources. And whether or not you enhance your existing transmission system or you add new lines to the grid, you're going to have to be able to be flexible in that transmission to be able to integrate all of those resources. And then also you need to have balancing resources. So with the new variable resources that are coming online, they tend to be a little bit more static. Either the energy is available or it's not. We're traditionally operated the system with resources that could go up and down to follow load. And you need to do that to be able to maintain adequate frequency on the system. And so it's been ironic. We've seen in at least in the 48 states and Canada that the transition to renewable resources has made us much more dependent on natural gas, because gas turbines have the ability to quickly ramp up and ramp down and can follow load in a more efficient manner than most of our other resources. So at least in the short term, we're having to add additional gas generation online to be able to accommodate the low and no carbon energy resources that have come. And then finally, we also need to make sure that we have a good supply chain, both from an energy standpoint and from a resource standpoint. So just to make sure that, we've got adequate energy that can come in, but then also a good supply chain for all of the parts that are coming in, and that they are cyber secure and that they are physically secure to come in. We at NERC pride ourselves on the fact that we have a very active stakeholder process. So our members are actively engaged in a lot of our technical and other activities and report into our board. So we have a committee, the Compliance and Certification Committee, that looks at how we perform our audits and gives us input from the entity's perspective about how we might be able to improve that, and how we might incorporate some of their ideas into our compliance program. We have the Personal Certification Governance Committee, which is the group that looks over how our system operators are certified. And they set the requirements for training, the number of hours that are required for that. And then they also develop the tests that each system operator has to take in order to become a certified system operator. Our large technical committee is the Reliability and Security Technical Committee. They are looking at both planning and operation issues, and then also cyber issues. But they are technical experts from broad industry input, and they have developed white papers and guidance And a lot of the white papers that you see on our website have been developed either directly by the Reliability and Security Technical Committee or the various subcommittees that report to them. The Reliability Issues Steering Committee is a group that produces a report every other year that looks at risks that are on the near-term horizon. So they look out in the 3 to 5 year range and say, what are the upcoming risks that we see that are out there, and how are we able to adapt and put some mitigation areas in place? So, for instance, the latest report that we did last year looked at regulatory risk and policy, energy policy, and how that might add to the reliability issues that are there. So would recommend, if you haven't seen that report, it really gives a good, clear idea as to what the energy executives in the U.S. and the provinces are worried to keep them up at night, the issues that they're worried about on the horizon there. And then finally, we have a standards committee that governs the standards development process and ensures that that is an open process too. Our standards framework also is a very open process. It is mandatory and enforceable to registered entities. In the U.S., it actually becomes incorporated as part of our law in the 48 by coming through FERC. In each of the provinces, and I'll explain in the slide a little bit later about how they're adopted in each of the provinces, but they're also mandatory and enforceable in each of the provinces too. It defines what the reliability requirements are in both the planning and operating, and then also the cyber areas. We organize them by topic, and I'll show in a slide here a little bit how that's organized. If you go to our site and look at all of our standards, sometimes you scratch your head a little bit to say, what does that 3-letter acronym mean? And so hopefully, if you have access to the slide deck later, you can use that as a quick reference for what each one of those areas are organized as. We also try to keep our standards results based. So rather than trying to dictate how somebody does something, we say what needs to be done, what's the outcome for it, and we leave it to the entity to determine basically how they do that, as long as they get the outcome that's required in the standard. And then we have an opportunity, and you may not see the need to do this up here, but we also have an opportunity for regional variances. So you have the ability to, in the West, if they're having certain issues that we may not be seeing in the East or in Texas or in Quebec, they can develop their own standards that are more restrictive even than what we're seeing in the rest of the areas. When I mentioned the standards families, here's a kind of a quick shop, if you will, for each of the standards that we have. We require, balancing, so that one looks at frequency response and the ability to balance load and generation, and then also puts the requirements for what you would do in your EMS system and the equations that you would have there for balancing your load and generation. We have an entire suite of critical infrastructure protection, which looks at both cyber and physical security, and then also supply chain. So all of those three are contained in that area. We have the COM standards, which talk about how you communicate. So not only requiring channels of communication between all of the entities, but then also stipulates, the language that would be used, the time zone. Some of those things you're not going to have to worry too much about up here because you have a common time zone. You may have a common language that you would already be using between your operators. But that ability is kind of set in the COM standards there too. And then foreign emergencies require 3-part communication between the operators. Emergency operations and system restoration basically is the requirements for how you do black start and how you test your black start, whether it's done physically on a test or a tabletop, and then what the communication protocols are required for in that. Facility requirements look at everything from vegetation management to how you do line ratings. The interchange requirements are a bunch of standards that actually we're on the process of retiring. It was more of doing interchange control, and those have been moved over to more of the marketing area. Real-time operations controls how reliability coordinators work with each other. We have a bunch of standards for modeling and how you collect model data and verify those models. We have one standard in the nuclear area, which basically talks about the nuclear plant interface and defines roles and responsibilities on each side of that. The PER standard looks at personnel training. So not only the system operator certification, but how other personnel are trained in your system. There's a suite of PRC standards, which looks at system protection, control, and maintenance. So looks at disturbance monitoring, missed operations, and how you do investigations for missed operations, how you do it, how you set up a system protection maintenance program. Under frequency load shedding and over frequency load shedding is also in that suite. And then the ride-through standards would be there too. The TOP standards are kind of a mirror to the IRO standards, but look at transmission operations and would apply to the TOP. We have a few standards in the transmission planning group. One of them, and I'll go through the details on that one a little bit later, TPL1, which looks at how what you need to do for steady state analysis and dynamic analysis. And then we also have a standard in the TPL suite that looks at solar magnetic disturbances, GMD, and what are the requirements for doing the planning in that area too. We have a couple of our standards which look at setting voltage control. We have, looks like I've repeated a few of those here. So after the VAR standards, those are a repeat. I guess it just looked good on the slide. For standards development, we have a standards process that guides how those are done. We ensure that it's a fair, open, and balanced process. We need stakeholder expertise. So we have standard drafting teams that are staffed by stakeholders that are experts in certain areas. They're the ones that develop the standards, that send it out for comment, and then look at the comments and do the modifications that are necessary for the standard as it goes forward. They actually do the drafting. We require for a standard to be adopted that it has a 2/3 consensus vote of all the folks that are basically going to be subject to that standard. Once it passes that, it's approved by our board of trustees and then filed with the applicable governmental authorities. And in the U.S., the 48, that's FERC. I'll explain a little bit later who that's done for each one of the provinces. And again, it's governed by this standards process manual. Just a quick slide to show what the process looks like, but you can see that there are feedback loops in here for where the standard is posted for comment. The comments are collected. It's posted for ballot, and then the do loops that are in there for that. Finally, you get to a final ballot and the adoption for that. We are in the process, I'll mention this right now, of looking at that whole standards development process. We're doing a modification of that. That's out for comment right now. In fact, we've got some webinars this week that are explaining to folks what the thoughts are for doing the changes in that. We're collecting some feedback on that process with the expectation that we provide to our board in February some projected changes to the standards process to make it more efficient. As it is right now, it can take us anywhere from, if we don't have a deadline, anywhere from 2 to 5 years to develop a standard, and we'd like to see that shortened significantly on that. We have a deadline, of course, that's imposed upon us by either FERC or one of the provinces. We work to meet that deadline, but otherwise it does take a little bit of time to get to consensus. In the standards themselves, we have 2 different entities that are referred to for planning. And I'm right now from here on going to be talking specifically about transmission planning. We have the transmission planner and planning coordinator. As you're looking at our standards, you'll notice that in the requirement language, you'll see certain things that are capitalized. If you see a capitalized term or a capitalized entity, you can go to our glossary of terms and see what the definition of that entity or that term is. So these are the 2, transmission planner and planning coordinator, and these are the definitions for those. You can think about the transmission planner as being kind of a local area planner. So it would be for each utility or each entity whoever does the planning for that particular entity. So they develop a long-term plan for the reliability of the interconnection electric transmission system within that particular part of the planning authority. So they're a subset of the planning authority area. Planning coordinator is more of a wide view. They look at all of the transmission planner plans that are developed to look to see whether or not it's a cohesive plan for all of their area there. And then they're also responsible for looking at certain protection systems and looking at resource plans there too. So just to give you an idea about what the transmission planner and the planning coordinator are. The standards that apply. Oops, I have a bit of a lag there, sorry. So there are specific standards that apply to the transmission planner. And I'll kind of step through what are the requirements for each one of these. So in fact, the transmission planner, which is looking at facility interconnection studies, it requires that the transmission planner study the reliability impacts for new or revised interconnections. And that's both transmission interconnections, generation interconnections, and now as we go forward, new load interconnections that could be there. Fact 14 requires that you look at system operating limits and develop a process for facility ratings for those, and then look for any instability that could occur as you're doing your studies. IRO requires that the transmission planners communicate their assessments to the reliability coordinators and develop solutions for any short-term issues that are found there. The MOD 26 standard is a verification of models and basically requires that you communicate dynamic model expectations to generators. So the transmission planner has to tell the generator, hey, these are the models that I need in order to be able to study your system. MOD 31, they got to provide the data. Basically, the entities have to provide data to the transmission planners that they need to be able to model the system. Data for system modeling and analysis, the MOD 32, basically sets out what modeling data requirements are there. The nuke plant interface coordination basically sets those requirements for the planner during that delegation that I mentioned earlier. Under frequency or under voltage load shedding, PRC 10, the transmission planner has to develop parameters around how they're going to access under voltage load shedding. TPL 1 basically gives the requirements for how they study that system, and I'll step through that here in a little bit. And then TPL 7 is the GMD standard that I talked about, and it also has the study requirements for that area. So now the planning coordinator standards. Most of the standards also apply to the planning coordinator, but I've highlighted in red here some of the additional requirements that a planning coordinator has to do. They, in MOD 33, have to develop data validation processes for steady state and dynamic system model validations. In addition to under voltage load shedding, they're also responsible for automatic under frequency load shedding. So they have to develop a process to study those systems to make sure that they're coordinated. PRC 12 is remedial action schemes. So they're responsible for any type of systems that are automated systems that aren't necessarily protection, but might be generator scale back or sympathetic transfer schemes to if a line is overloaded, it would do an automatic system to either back down generation or do some transfers on the transmission system to relieve that. Transmission relay loadability, they're required to specify what the relay loadability limits are for each one of the relays. And then they're also expected in PRC 26 to ensure that load responsive protective relays don't trip in response to stable power swings during non-fault conditions. So they've got a few more responsibilities in those areas. TPL 1, which is the main transmission planning standard, has requirements in there that makes sure that system models represent all existing facilities. For the next 10 years, any new planned facilities and changes to existing facilities that will be there. It also requires you to have real and reactive load forecasts, and then any known firm transmission service ability that's in there, and any interchange that you're known for firm need to be included in those models. And then any resources that are required to supply the load. They also are required to perform and document a planning assessment, which looks at both steady state analysis, short circuit analysis, and stability analysis. And then they have to provide that information to entities that request it and that need it for a reliability reason. You have to look at both near-term and far-term studies. So the near-term would be in that 1 to 3 year range. A far term would be in the 5 to 10 year range. There are specific contingencies that have to be studied. So certainly N-1 generation outages, and then there are some extreme contingencies that are also listed that you need to study. For the N-1, you've got to stay within acceptable steady state voltage limits. You've got to make sure that you've got to stay between any post-contingency voltage deviations, and also that you have its transient voltage response that's specified there too. You also, under N-1, cannot have any transmission overloads or any islanding that's uncontrolled for that area. For extreme contingencies, you might have a corrective action plan that requires the operator to take action, but you wouldn't necessarily have to construct for any of the extreme contingencies that you study there. And then again, like I mentioned earlier, you have to provide the results to any functional entity, any entity that has a reliability related need to have the information from those studies. When you look at the differences between the 48 states and each of the Canadian provinces, there are differences there. Certainly, we in the U.S. file all of our information with FERC. You can see with each one of the connected provinces who that entity is that we do. Within Quebec, it's filed with the REGI. Most of them, it's filed with either the energy boards or the utilities commissions for each one of the provinces. How long does it take to adopt? That is determined by statute, basically within each province. In the U.S., there's an implementation plan as it's approved by FERC. It kind of specifies in there when it's adopted. For each one of the provinces, some of them do a quarterly or an annual process, and then some of them are throughout the year as we file it with them. Some of them also are an automatic adoption based on when the NERC effective date is. So it kind of depends on the province itself. There's also some other variations there that can be done on a province by province basis. And then I mentioned here who the regional entity is for each one of those, which is, WEC, MRO, and NPCC are the only three that have connections to Canada. The question then comes up, okay, well, then who's responsible for auditing and doing enforcement and mitigation in those areas? In most of the provinces, the auditing is done by the regional entities, so either WEC, MRO, or NPCC. In a few of them, it's actually done by the province itself with our review and input from those regional entities. And then, as you can see, in some of the provinces, they allow for financial sanctions, and some of them they do not. And the reason for that is in some of the provinces, the responsible entity is a crown corporation. And so in that case, it kind of makes it difficult for one governmental entity to find another governmental entity. So rather than there being financial sanctions, there's other ability to require things to occur on the system. But as you can see, most of them do have financial sanctions that are allowed. In the U.S., this has been updated based on inflation, But when we first established it, the maximum penalty could be up to $1 million a day for each infraction. That number has escalated a little bit by inflation, but kind of is a pretty good rule of thumb. Before we get to question and answers, there are a few things that we're looking at now that I'm sure would be of interest to you all. Also, we are in the process of developing a suite of standards that look at inverter-based resources and how we connect and study both wind, solar, and batteries. And so that is on the table. We have drafting teams that are looking at that. And then, we're also looking at the new loads as they're coming on the system. We have a large load task force that has a white paper out describing large loads and data centers and their effects on the system. We've had a couple of events that have occurred with some of these data centers, one in 2023 and then one earlier this year, where we had single line to ground faults that were cleared in normal times on the transmission system, but knocked off 1,500 megawatts of load, which all occurred on the load side, not on the entity side. So they automatically switched over to self-generation. And part of that was because of inverter-based resources and the fact that the inverters went into that mode to ensure that they would have adequate cooling. When you think about that, I mean, that's 1,500 megawatts. That's the loss of 1.5 nuclear plants, if you will, on the system. So it was something that certainly was unexpected, and most those occurred on the Eastern interconnection, which is a pretty stable interconnection, but it was enough to open our eyes to situations. There are a few entities right now that have received interconnection requests from new data centers and AI centers that are looking at single points of interconnection that are in the 1 to 2 gigawatt range. So if you can think of, the entire load of Alaska, or as we refer to it, the 48 states, kind of a load the size of the city of San Francisco, all connected at one point, and all also inverter based. So it means it has the ability to come on or off the system and look like a step function. We need to be sure that we study that, understand the implications, and see if there's any reliability things that need to be done in order for those loads to be connected. That's pretty much what I have for transmission planning and for the standards process, and a little bit of an overview of NERC, and would be open to any questions that folks might have.
Fantastic. Thank you, Howard. We do have a couple questions in the chat. People feel free to drop more questions in there. So the first question we have is from Brian Crowley. Is there a reliability requirement to determine anti-terrorism protections against large transformers and critical utility infrastructure?
Good question. And what we have is we have a physical security standard. I'm trying to remember right now. I think that's SIP 12 or SIP 14. I get the numbers mixed up, but we do have a physical security standard in our SIP suites. And it requires basically the transmission planner to do an evaluation of their systems and look to see whether or not any piece of equipment or a loss of a single substation would result in voltage collapse or unintended islanding to occur. So yes, we do have standards that require that study, and then mitigating effects. So if you find a substation that is critical, if you will, it meets the definition of that, then they're required to come up with a place for protection, which may involve anti-ballistic screens around the outside of the substation, may require some things to be done inside the substation too.
All right. And could you remind us, sorry, which suite of standards that was in? That was in the SIP standards?
In the SIP standards, yeah.
Okay, thank you. Our next question is from Peyton Reed. You mentioned a white paper on large loads. Are there standards under development for large load connections too?
Not currently. So what we're what we're trying to figure out is what would those standards look like, and then who do we think is the most responsible person for that? So who would we go out and register to make sure that they know that they need to be applicable to the standards, and make sure we get the right people lined up for those requirements. So that's the first step that that large load task force has taken, and that's what the white paper deals with, is looking at the issue and try to determine, based on our existing suite of standards, where are the gaps, who should be registered, and what should the standards look like.
Gotcha. Great. Well, I have a question for you, and also people feel free to jump some more questions into the chat. Do you have recommendations for folks in Alaska who are currently working on several of these standards that you've gone through? You know, if you were like knowing everything you know now and the history that has happened, like, are there a couple of those standards you like know off the bat, like you would recommend like changing, adding, removing parts of for a system like ours?
Yeah, so I mean, I think you could start with the TPL-1 standard, which is that basic planning standard. There may be some extreme contingencies in that in one of the attachments, the tables and the attachments, that wouldn't be applicable up here, certainly. And then I would also, as long as you're in the formation of your development of standards right now, I'd give serious consideration to making sure that you understand IBRs and the modeling that's required for IBRs to get into that. We've been, by waiting as long as we did, we're a little behind the 8 ball here. So I think it would be helpful to get that early with all the other standards there in your suite. We found that the longer we wait on that, the harder it is to deal with legacy pieces of equipment. So would encourage in that area too. And I think if you're looking at developing cybersecurity standards, it'd be good to sit down and talk through that. Our paradigm that we started with, and we started developing these SIP standards back in the 2005 timeframe, our standards basically require you to go through and do an assessment of what are the important things on your system, and then what are the cyber assets that control those. And then, you want to make sure you have an electronic security perimeter around those, and then a physical security perimeter. So protect the assets, and then also make sure that you can guard against folks coming in. That paradigm breaks down when you start talking about virtual machines and when you start talking about operations in the cloud. And one of the things that we're struggling with now is how do we take that existing SIP paradigm and apply it to some things that I can't put a physical security perimeter around because I can't touch it. I can't feel it. It's not in a physical location. Same thing with an electronic security perimeter. It may be a virtual machine, and it's a little bit more difficult to do that. One thing that we've done in our most recent version of the standards is accommodated virtualization by switching a little bit more to a zero trust form rather than doing the ESP and the PSP, the electronic security perimeter and physical security perimeter. I think I would also make sure that it's important to look at transmission planning, but it's also important that folks understand how to respond to emergencies. So there's some of those standards about developing a black start plan and making sure that you exercise that, if you will, either a tabletop exercise or, attempting to do some black starts occasionally from different units. And then making sure that you've got a good communications plan there, that all your operators can talk to each other. They understand, how to interact and can work together in restoring the system. And then I would also look at those bow standards, because that's very important about keeping load and generation balanced and maintaining your frequency that's necessary So having an understanding in all your EMS systems doing the same calculations and making sure that you have the ability to recover from an event within a certain time frame, and then also making sure that you maintain, your system frequency within certain bounds.
There's a lot of topics, a lot of recommendations there. We'll probably be reaching out for further advice on that. I have a quick question going back to what you mentioned earlier about recommendations for getting started on incorporating what NERC is working on right now with IBRs and working those into TPL standards. Do you have recommendations on how to do that, given NERC is currently in the process of doing that themselves?
I would say my best recommendation on that would be to have folks follow those drafting teams as they're working on it right now. All of our meetings are open. They're posted on our website and certainly open to the public for anybody who would want to join in on those. So you can also you'll see on those drafting team sites, you can sign up for the email exploder on that. So any work that drafting team does, you can get information from that, even if you're not able to join the calls. And so you can see how they're iterating through those processes. I would recommend following those very closely and then seeing how those should be adapted when you're doing your development of your standards. The conversation that you heard just prior to mine, the presentation about EMP studies, that's critical. And I think it's going to be good to, the nice thing about your system is I want to call it compact, right? You don't have a lot of external connections. I think you can get a pretty good handle on it and develop a pretty good model for it. You'll have a good ability, I think, to develop those EMP models and be able to study those generators well. We have found that a steady state model of these resources gives you a good idea about how things operate in steady state, but they don't really look at the small signal issues. And so having the ability to examine those small signal issues and being able to see if there's other things that need to be put on the system to help accommodate those is good. I think we're going to get some good information out of the event that occurred in Europe earlier this year, the Iberian Peninsula, and seeing what actually we can learn from that. And then I know that there was some issues down in Chile late last year, early this year that I think we can learn from too. But we're trying to incorporate that information into the development of our standards.
Awesome. And I know I'm supposed to move to the next presentation, but I'm going to sneak in one more question before we move to the next. So this question comes from Mari Shirazi at the university. What are the synergies and potential overlap, if any, between the NERC standards and the IEEE standards, such as 2800?
Really good question. And one of the things that we're proud of, I don't know if I can really use that term right, but we had folks actively involved in the IEEE standards. When you think about the difference between IEEE standards and NERC standards, IEEE standards, for the most part, are written more for the pieces of equipment, the specifications for how the equipment is designed and how the equipment is supposed to operate. But it also requires, when somebody buys that piece of equipment, that they specify that it has to be compliant with that IEEE standard or that particular version of the IEEE standard. Our standards are more about performance standards for the system and performance standards for entities. So when you take both of those together, so like the Durham standard or 2800 or 1547, they are dealing with equipment design parameters. If a transmission planner specifies that those design parameters need to be incorporated into the system for them to do their studies, then you've got a nice synergy between those two. But yeah, we had folks actively involved in the development of all of those standards to ensure that our standards and the IEEE standards would work together as a cohesive unit to ensure reliability.
Awesome. Well, thank you so much for your presentation and Q&A. Right before we go to our next presentation, Andrew has an introduction and has a quick announcement to make before we jump to the next presentation. I'll go ahead and take over.
All right. Well, thank you, Felicia, for all your work today, and to the speakers. It's been really educational once again. So do appreciate that. I do have to take off a little bit early before the end of the thing, so I wanted to jump on and just share a real quick announcement. We do have our dates locked in for next year's Alaska Sustainable Energy Conference. And so it will be May 19th through the 21st. 2026. That will go back to our previous week that was before Memorial Day. So mark your calendars, and then certainly go to alaskasustainableenergy.com, scroll to the bottom. You can sign up for conference updates, although many of you are probably already on that list. But we certainly anticipate this will make things a little bit more logistically easier for folks to not compete as hard with tourism season. So we are excited to move back to those dates and to announce them today. So mark your calendars, save the date, and thank you once again for being here today. And with that, I will give it back to Felicia.
Great. Thank you, Andrew. All right. So now to end our workshop, please help me welcome Ken Aramaki and Lee Yu from Hawaiian Electric. Ken is the Director of Transmission, Distribution, and Interconnection Planning at Hawaiian Electric Company. In this role, he leads a team that plans for the future of the T&D system as increasing levels of renewable inverter-based resources are added to the grid. And I'll also introduce Lee Yu. Lee Yu joined Hawaiian Electric as a transmission planning manager in 2021, and served as an active member of the IEEE 1547 revision working group and the IEEE 2800.2, and a standard draft team member for the NERC PERC 30-1. Welcome to both of you. I'll let you take over. Thank you.
Thanks, Felicia and everyone for having us. Again, I'm Ken Aramaki. I'm the Director of T&D and Interconnection Planning. Myself and the Manager of Transmission Planning, will be tag teaming this presentation. So a little bit about Hawaiian Electric. So Hawaiian Electric, for those that don't know, we operate across 5 islands. That's Oahu, Maui, Molokai, Lanai, and Hawaii Island. These are all 5 non-interconnected grids. Oahu is our largest load center with 308,000 customers. And then Maui County, which comprises of Molokai, Maui, and Lanai, has about 73,000 customers, and Hawaii Island, 88,000 customers. So Oahu peak demand is around 1.2 gigawatt. Maui County and Hawaii Island around 200 megawatts. We are on a path to try to get to 100% renewable energy, or very high levels of renewable energy. As of 2020 and end of 2024, our consolidated renewable portfolio standard is 36% across all of our service territory. Oahu is at 31%. Hawaii and Maui County are a bit higher. And at instantaneous levels, Hawaii and Maui reach around 85+% renewable energy. Our overall goal, 2045 goal, is to reduce carbon emissions to net zero from 2005 levels. And that's really the driving force behind like a lot of our planning. At the end of 2024, some kind of key metrics and things that maybe differentiate us from other areas. 43% of single-family homes have rooftop solar, so we have a high penetration of DER on our system. We also have, on the bottom left, AMI was only recently kind of done at scale on our system. So at the end of 2024, we have 95%. And then on the bottom right, because of our, I don't know, there's a lot of factors that kind of contribute to it, but for last year's rooftop solar, 94% of it that was installed came with also battery storage. So I mentioned the driving kind of the overall goal of getting to net zero by 2045. We needed to create a plan that gets us to that kind of very aggressive goal. So in 2018, we started what's called the IGP, the Integrated Grid Planning process, which everyone kind of talks about now. We've done it in kind of 4 stages: data collection, where we've looked at all the kind of forecasting things that we're going to take into account, creating our assumptions. Then with that, we started to define what our plan is going to look like. That's where like a lot of the modeling comes into play. And then we created a plan, which so we started in 2018. In 2024 is when our commission accepted our plan. And so with that plan, we're now we're working towards implementing an RFP to obtain the resources needed to meet that plan. And then we go into plan refinement, which is to update the plan based on what resources we start to get within our RFPs, and then we're going to continue to iterate on that. Across all of these pillars, we've included community engagement. So I think that the key piece of this is that throughout the process of the integrated grid plan, we worked with community stakeholders as well as more technical stakeholders within the state to get towards this plan and get buy-in throughout the process. This is kind of I would say it's a little confusing flow chart, but if we start from the top left, so this is the overall modeling process that we used for integrated grid plan, and it's pretty similar to other areas. So we start with capacity expansion planning. So with the capacity expansion planning, we're looking at an initial resource plan with and we used a base case, which was developed through our integrated grid planning process, with stakeholders. And then we also looked at a land constraint case. So what we found was if we utilize basically to get to 100%, especially on Oahu, we have limitations on how much land can be used. And so even if we maximize all the areas that are even available to build on with solar, essentially, we barely get to that 100% goal. So with a land constraint case, it's a combination of utility scale resources plus an aggressive DER increase. So more rooftop solar, rooftop plus battery resources on the system. With those initial resource plans, we then move into our resource adequacy analysis. So that's we use Plexus to do that, and that's looking at the reliability of the system with the resources online. Then we go into production cost simulations to looking at what the overall portfolio could or would cost relative to other scenarios. And so in this case where we're finding what resources could be on the system, that's an iterative approach with our system security analysis. So this part needs to be tightly coupled between our generation planning folks and our transmission planning folks. And I think we've done a couple of iterations of this on different plans to look at out of the production cost simulations, what kind of security concerns do we have, and then including some of those assumptions of what resources need to be online or what constraints need to be online, and feeding that back into production cost simulation. In parallel to that, we also have our distribution planning, which distribution analyses or grid needs was a little bit more challenging to incorporate into the overall integrated grid planning needs. But what we did look at was, okay, based on what the DER forecasts are going to look like, and the net result of DER and load growth on our distribution system, what kind of upgrades are required to meet those needs, and also what kind of NWAs exist to address those needs. And so all that comes into kind of converges towards the system security analysis, and then it goes into our final grid needs portfolio, or what we call currently our preferred plan. And so our preferred plan goes from 2030 to 2050, and that's adding resources across different levels. So adding utility scale resources, which are shown on the top, like the additions. And then we have DER additions, which is, we call DER, what we refer to DER is rooftop solar, essentially, rooftop solar plus battery storage. And then on the bottom is what fossil fuel generation we plan to deactivate. So there's going to be like a counter or a complementary addition to resource reduction, and the additions are going to need to be much more substantial in terms of megawatts when looking at variable resources. So just as an example, so between now, or it says today to 2030, that stack is showing what we're doing is stage 3 RFP, which is looking at trying to bring into the system 540 megawatts of firm renewable, as well as 801 megawatts of hybrid solar plus wind resources. I don't think we've met those targets, but which just means that we need to incorporate that into the next round of procurements and adjust that. But again, a substantial amount of resources that we need to be adding to the system to get to these goals. And also DER, growing the DER another 220 megawatts between now and 2030. And then, getting to 2050 to essentially get to the CO2 emissions of negative 92%. I mean, getting to that 100% is very, very difficult, but at least, getting to 90, 95, or, in that realm is a huge benefit for our state. We started our major procurements for these inverter-based resources or renewable energy resources, which happen to be mostly inverter-based resources, started off with what we call our stage 1 projects. This started in 2018, and as of just, I think, last month, we completed all the projects that were selected or that made it through selection and development process in that entire pipeline. So on Oahu, we added 139 megawatts of PV plus BESS. On Maui, 60 megawatts of PV plus BESS, and on Hawaii Island, another 60 megawatts of PV plus BESS. Obviously, our state has a lot of sun potential, so that's why a lot of our procurements yield PV plus BESS. In stage 1, because that started in 2018, those are all grid following plants. In what we call stage 2, which started in 2020, so we did a procurement. We did a procurement in 2018, and then before those projects were even getting into like the engineering phase, we started another procurement round, and this is what we call stage 2. And in 2020, we realized, well, around that time frame, or around the study time frame, we recognized that grid forming was kind of coming out and was going to become something that our system may require, essentially, because of the large amounts of inverter-based resources. So from 2020, even through now and in the future, all of our utility scale plants that come onto the system that include battery energy storage, also it is required to have grid forming controls. So on Oahu, we added a what we call KES, or Kapolei energy storage. That's shown in the picture on the top. And that's 185 megawatts of standalone BESS. And that's 135 megawatts of grid forming, which is used for load shifting, and then also 50 megawatts of FFR. So it has a dual function, and really helps in terms of like to help with our contingencies, because again, on Oahu, system is 1.2 gigawatts. This battery is essentially almost 20% of the needed generation. And then the other, I guess the main one of the biggest benefits of grid farming is, well, on our system, a major risk is the grid falling resources that have that momentary cessation, or issues with may have issues with ride through. Those plants are PV resources, or which is a lot of our mix. At the peak is during the day, and at that time, our standalone storage is also charging during that time. Most times, and if there's a contingency that takes offline the PV resources, we have a plant that is in charging mode and then can respond quickly from charging into discharging, so it can provide effectively even more than 185 megawatts or 135 megawatts of response. We haven't seen that much of a delta needed yet, but we have seen that this Kapolei energy storage project has provided a lot of stability benefits to our system. In addition to that, we have Kupono Solar, which is another PV plus BESS, 42 megawatts grid forming resource. And then we have other projects in progress. Okay, so now I'll hand it off to Lee.
Okay, thank you, Ken. Can you guys hear me? Okay.
Yep.
Thanks so much for the opportunity here. And you guys may see this slide before in Ken's presentation. This is basically the high-level flowchart for our integrated grid planning process or study process. And the transmission planning is sit in this red frame here. And it starts from production cost simulation there. So most of the input to the transmission planning process come from production cost simulation. And we take hourly simulation result from there, and also we get a system level load forecast information from there. And we also get locational load forecast information from load seer software from decision planning. So make sure we capture both system level load growth as well as specific special customer or locational load growth in our transmission planning model. And after we got all those information, we start similar like what mainland folks do, start enter into the steady-state analysis. We perform the PSC and then dynamic stability analysis. Since recent year, we do those hosting in the PSCAD. And after those study, we will evaluate the study results against our planning criteria. If there is planning criteria violation, we normally will go back to the resource planning process, working with resource planning guys to see if we should add any resource dispatch constraint, or we should do wider solution, such as transmission system expansion or transmission line upgrade, to see which one is better to fix the criteria violation. After the iteration, and we get updated input from production cost simulation with considering all those constraints and the future transmission system investments, and then we do evaluation again against the planning criteria until we get everything complying with our planning criteria. We generate this final grid portfolio, which is our preferred plan. We'll go to the details of the transmission planning process in future slides. So next slide, please. I want to use this MAUI system as an example to show what kind of the changes or challenges we're facing during this energy transition. So in this slide, left-hand side shows a MAUI system like 15 years ago, what it looks like. So the whole MAUI system transmission level voltage is 69 kV, and it has sub-transmission level 23 kV, and then remaining at distribution level. The whole MAUI system mostly supplied by two power plants in this two green box. So the south side of green box is the 69 kV Malaya power plant. This is the only one power plant on the 69 kV. And then the north side of the central Maui is the Kokolui power plant, which is the only plant connected with the sub-transmission system. That's all, and it's pretty simple and clean, I would say. And the right-hand side shows within 10 years, this kind of future, I would call it a short-term future, what Maui side grid scale power plant looks like. So you can see the green box still there, and actually the sub-transmission level north side of green box will be retired, become a synchronous condenser plant. And that 69 kV south side green box plant will also have partially retirement there. We'll only keep a few dual train combined cycle there. And around 10 years ago, we added 3 wind power plants into the Maui system, basically are in that blue box. And as Ken mentioned previously, we also add a 60 megawatt PV paired with BESS plant, just on the north side of the Malaya power plant. All these are in the blue box. And in addition to that, we get approved projects and awarded projects in recent stage 3 system resource RFP. So you can tell that the whole system landscape has been totally changed. So the fossil fuel power plants are getting gradually retired, size becomes smaller and displaced by the dispersed IBR plant or renewable plants across system. And changing power plant number from 2 firms to around 10. Most of them are non-firm plant, variable plant, or with a 4-hour battery duration plant. The system generation dispatch in future change, increase variety increase exponentially, and the transmission system, the flow pattern will be very different than 15 years ago. Also, we need to consider that system loads keep growing. So the EV come into the system, and it makes that the transmission planning now is quite different than many years ago. Where definitely we're facing way more challenging here. Next slide, please. To address all these kind of challenges, we also adapt our transmission planning process to this new paradigm. So in the state part, basically this slide shows high-level process of how we do state analysis. So we still keep doing the snapshot power flow study, which address in traditional way like peak load condition or mean load condition. We also look into those plant or a group of plant deliverability. Basically, we need to make sure that the plant can deliver their contract capacity when system need them most. So we address those in the multiple snapshots, multiple scenario, zonal type power flow study. In addition to that, because we really do not have very clear picture about how in future system will dispatch those variable resource. So we have to consider all those information comes from production cost simulation. We use those hourly dispatch data to run time series study for study year. So basically we run 8760 study for the whole system, and every single hour we run full set of contingent study. In addition to that, we also evaluate during the extreme weather condition, such as really long duration days with very low solar energy production. System may need to use a battery to do things more than they normally do. So we got those extreme weather profile and got production simulation data from, with this extreme weather condition, and also run time series study to make sure transmission grid has enough capacity to let system dispatch in that way. And we look into all this snapshot study, time series study results, and comparing, with planning criteria violation, identifying, comparing with planning criteria, identifying if there's any violation, and we look into system expansion. So if certain location, we do see, the best solution is just to change the conductor from 36 to 506, then we should do that. We initialize project. We also look into maybe certain location, the generation, they have a lot of generation right there right now. There could be some constraint, and the constraint could be really temporal because they are all variable resource. So we work with resource planning folks to see how about implementing certain dispatch constraint, if that works, or if that looks like more economic in short term. And also we look into the grid needs. In some of our system, sometimes the study results really sensitive to the location, and we may not have super strong cross-island tie to move energy from one side to other side, especially, consider the Hawaii Island, which is pretty large. So maybe it is more important to have resource locally to support local load growth, to support local voltage stability and try to avoid cross-island energy transmission. Yeah. Next slide, please. This is about the dynamic stability study. So we've been using the PSCAD or EMT environment for dynamic stability study for a few years. And this also starting from production cost simulation. We look at those hourly dispatch data and run some statistical analysis, identifying typical scenario. And also by using past study experience, we consider, certain dispatch scenario or very high risk dispatch scenario and certain contingency probably pose high risk contingency. We use PSCAD to look into those scenario. Before we're using PSCAD, we're using PSC, this kind of software to run dynamic stability. In that kind of environment, we can run a whole set of contingency and look into many dispatch scenarios. Now the simulation speed is maybe thousands times slower. So right now we cannot afford to run every single contingency, to look into every single dispatch scenario. So we have to utilize the past study experience and the findings. Right now we try to first look at the high risk contingency, high risk dispatch scenarios, and then gradually expand. For example, right now, as Ken mentioned, that we have DER, we have a lot of DER. They're not cannot be directly controlled right now or curtailed. So we see from many studies, we see that during the daytime, high DER generation time window, when system has least firm resource, that could be a really high risk dispatch. So we spend a lot of time to look into those kind of dispatch. Evening, we see, definitely we cannot ignore it, even though right now the risk is lower. And important finding of recent study shows that, with grid forming resource on a system, we do see there's hope that system stability can be improved while we do this energy transition, while we keep taking the DER resource and the IBR resource in the system. But it is really important to make sure there are headroom from those grid forming resource to respond to system event. Most of the time we have system event with under frequency issue and with can potentially with voltage recovery issue. With sufficient grid forming headroom in the system, this issue could be effectively mitigated. So grid forming headroom requirement is really important dispatch constraint that we generated to, or backfeed to the resource planning folks. Next slide, please. Some detailed information about our system stability challenges. So we've been seeing this in field and also in the study. So first one is the legacy IBR Radisson performance issue. As Ken mentioned before, we have some standalone wind farms or even some PV paired with BESS, this kind of IBR facility. They have some fault restoration issue. This are very, very similar as what we know from Texas Odyssey event. In this slide, on the right side upper corner, this plot, this is from field event. So we have a transmission level 3-phase to ground fault on Oahu system, which is 138 kV system. And that system, because at that time, all the online IBR going to moment cessation or going to, you can see those crazy up and down. Yeah, basically, system frequency in this red curve, quickly quickly go to below 58.7 hertz, trigger 2 stage of load shedding. Yeah, every single IBR in this event going to moment cessation or going to unexpected behavior. And yeah, we didn't see this in our study because later find out that all those model have issue. I think several panelists that, in today's meeting mentioned about that. And the DER moment cessation, which can be represented in the lower figures. So basically when voltage at a DER terminal or their applicable voltage of DER drop below a certain threshold, DER stop generating active power. And after voltage recover above threshold with a certain delay, DER start recovering active power generation with a ramp rate limit. And that form a huge megawatt gap because we rely on that there's more than 50% of generation megawatts coming from DER in the high DER generation time, and that gap, which caused by the DER recovery from moment cessation, can drive system frequency decline quickly. And since we have a firm machine dispatch the less or retire, we do see in the study that roll off could become much larger than what we see in real life event. And we also see the critical clearing time become shorter. Yeah, we're gonna need more. We're gonna need communication, dual pilot communication, or more transmission line to avoid zone 2 clearing. And with DER penetration level increase everywhere, we also see that our under-frequency load shedding system effectiveness get reduced. Right now, our commission approved a project for us to do Oahu load shedding system transition from static scheme to a dynamic scheme. But basically, we will need more load in this load shedding program to help maintain its effectiveness. The last thing is about the IBR model issue. So I'll talk that later in later slides, but we do see, there's a chance that the IBR get commissioned in a system, and during the commission, the folks doing commission who totally not aware of IRS study the settings and just use default OEM settings. And apparently, our interconnection study find out that normally or most of the time the default IBR settings won't work. We need something special. Yeah, and next slide, please. We're addressing all those stability challenges right now and trying to look into many different ways in the same time. So we mentioned before the grid forming resource procurement, which is a really important one. So starting from stage 2 RFP, we require all the IBR facility. The first pair with the best resource, and then the best need to be grid forming best. We do not take grid following controlled best. And optimize the grid forming resource headroom during the daily operation. So we try to have enough headroom from grid forming resource to respond to those large contingency, and address the DER moment cessation issue. Right now, our tariff use category 3, 1547 category 3 DER right through. performance requirements. In their under voltage limit for moment succession is 0.5 per unit, and that is too high for us. Right now, we're working with 1547 standard working group, proposal category 4 type of DER with moment succession under voltage threshold drop to 0.1 per unit. So yeah, this is what we're trying to work with them. We obtained a lot of support from the OEM, so we're confident that this new category will be in the next version of the standard. And as I mentioned before, we are addressing under-frequency load shedding issue right now, try to converting our static skin to dynamic skin, and align with the most recent NERC stage 3 alert or level 3 alert for the IBR resource. Yeah, we put more focus on the model validation during the commission and the post-commission. So basically, we need ask the generation owner folks to provide confirmation that the model control setting, what control and protection setting that we studied in the IRS is are implemented in the field. Yeah. And also in the post-commission, when there's system event, we get all those DFR data to run model validation. In this figure, in the slide, it shows that another system event, when system has a large generation trip, which causes frequency quickly decline, and this gray curves shows our right now the transmission level grid forming resource response, and we also have a grid following resource response to this under frequency event, and the machine response to this under frequency event, and you can see that the grid forming one in the first, I would say 4 seconds, the output is much stronger than the remaining resource. The grid following one strictly stick with the PFR group settings. I think that is expected. The machine one, maybe because of the aging issue, response width, we can see the inertial response there, but the PFR response is much slower. So yeah, so this is what we really need to rely on in our future system. Next slide, please. This slide shows system voltage and frequency recovery or dynamics during a very extreme system event in almost today's system and the future system. Assume all those resources got procured according to the plan. So basically, we can see that both voltage recovery and the frequency stability got improved a lot by getting enough grid forming plants into the system. Yeah, but it's a big question mark about eventually how many plants we're gonna get. Next slide, please. This is basically a summary of our transmission planning process in the IGP framework. So most of the input starting was the resource planning, and there it drives the transmission planning study model update, running both steady state and dynamic study, and typically we considered both wired and a non-wired solution to address all those planning criteria violation. And the wire stuff definitely is about the network expansion, adding more transformer, adding more lines. And the non-wire part is more about dispatch constraint for those variable resource and headroom requirements, and also the future system resource procurement. The grid needs drive the future resource procurement, such as locational needs or stability needs, this kind of thing. Yeah, I think starting from our next stage of the procurement, we call it IGP procurement, we will have specific call out the grid stability needs in this procurement. Next slide, please. About the interconnection, as I mentioned before, our interconnection starting from the system resource RFP. So once RFP opened, call out the specific grid needs such as energy needs, stability needs, and then we receive bids. And they're not only have the package about what kind of the project or facility we'll talk about, but also they will submit some initial models, including the protection model, PSKR model, PSC model, everything. And we will evaluate all those bids and perform the group evaluation or cluster study, because system small, we always do cluster study, to look into the steady state protection and dynamic stability analysis, and to select the best portfolio. And after that, we're doing the serious interconnection requirement study. In there, we determine if there's any steady state issues or dynamic issue. In the dynamic stability study part, the most of the time is spent in the control tuning for those IBR. Yeah. Once again, so most of the time, the default IBR control tuning does not work for us. We need to spend a lot of time with developer, with their OEM, working on how to optimize their control tuning. Once all this done, then we do there's long process until start doing the commissioning. And in the commission, starting from commissioning, we do model validations during the commissioning and also post commissioning. All this information are openly available in our RFP site in HECO's website. Yeah, I believe. Next slide, please. Yeah, I think as previous panelists mentioned, the model requirement or model review process is extremely important in all those interconnection process. And those are also the part of the important foundations for the planning study. So we published our model review process. In there, we talk about what kind of we provide a checklist for the model submittals, and then list the specific requirement for the steady state and dynamic model, provide the standard model test for the IBR model, both GFM and GFL. And also, we try to provide example model test package in our EMT environment for our future bidders. Hopefully that will help them to save some time for this model preparation. Meanwhile, we're working with National Lab under DOE funding, try to develop the black box system-wide real-time digital simulation model. Try to provide more tools for developer to optimize their project control before we kick off the interconnection requirement study. So, which means not starting from the default OEM settings, instead some control settings that really work for our system. Next slide, please. yeah, this is some model validation examples. So we do basically the left-hand side plot shows the model simulation results compared with the DFR data from a real live event. The red is the measurement, the blue is the simulation. And we see there's a slight mismatch, or there's certain degree of the mismatch. So we talk with the generation developer and asking, and also OEM asking about the gap. And it turns out that during the model revision, certain modification got lost. And so after they recover the certain settings, control settings there, here I think specifically about the PFR settings, and the model match was the real life measurement much better. But I do want to say that this case is just a generation trip case without any faults. We did look into a fault event that model match or model benchmarking process is way more complicated than here. Yeah, this is too many external factors or uncontrolled factors there. It's not easy, or it's not always get a very, very good match in both P and Q. Yeah, I would say that. Okay, next slide, please. I think this is the conclusion part. First of all, the energy transition, yeah, it's been a lot of challenging as well as fun for transmission planning, is at least for us. Yeah, there are a lot of interesting topic now, and it do trigger a lot of workforce training needs, at least in our company. And we do see that it makes much more sense to consider transmission planning under this whole IGP framework, maximize the resource capability. Yeah, and the interconnection process really need to align with the transmission planning process to make sure approved planning recommendations get implemented through the interconnection process, but not just stay in the simulations in the models. This also makes sure that our model always reflect what happened in real life and make our planning studies make sense or real. Thank you.
Fantastic. Thank you so much, Ken and Lee, for your presentation. We do have some questions for you guys, so I'm going to get those started. All right, so first question on deck is from Jean. Earlier this year, Governor Green tasked the Hawaii Electric Office to develop a new strategy to address electricity costs and the increasing unreliability of Hawaii's firm power generation. This is envisioned to utilize LNG and a shift from the 100% renewable energy goal. Is this shift due to aging thermal generation or a need to have more responsive generation to firm up renewable energy sources?
I'm not sure like what the driving factor is. Our speculation, or my speculation is, they looked at our plans. We do have like a lot of PV plus storage and wind resources that are needed to get to that 100%. I think they saw that there's a lot of risk to getting all those systems online. Also, the risk is that as we've gone through our RFP stages, there has been projects that start to be developed and then they withdraw. So there's a lot of risk in that. And so this is more of a diversification and looking at other alternatives to get to the 100% goal.
Gotcha. Thank you. I'll jump to the next question. As from Dave McTosh. Is the underperforming PFR from existing synchronous generation creating challenges for IBR integration, even with grid forming capabilities?
I think right now from system event looks like we are okay. Yeah. The long term run, I mean, after I think in the plot which shows how many seconds, which shows 12 seconds. Once we move the curve longer, the machine's output starting coming back to the PFR expected PFR curves. Yeah, and I think that's some issue that we need to pay attention, but it's not right. It's not on our top list right now.
Right. Okay. Thank you. Our next question comes from Mari. Does HECO or even the wider community have guidelines for what stability issues can be addressed by grid forming IBR versus synchronous condensers? Are EMT studies required in both cases?
The main drive of the EMT in our system first come from the grid forming resource. When we start looking into grid forming resource during the stage 2 resource procurement activity, we find out that the LEM could not provide really good positive sequence model for dynamic stability study. But they can provide really good the EMT models. So we decide to use EMT since then. If we only looking at the condenser and the system mostly only have a machine and some DER, and we only look at the balanced fault, I think maybe positive sequence should be okay. But once we need to look into the IBR and we want to unlock IBR's control or unlock IBR's potentials, I think we have to use EMT. The other question regarding the difference between the grid forming IBR and the condenser, the condenser has a strong overcurrent capability, provide a strong dynamic VAR capability, can reduce the roll off, but cannot change the frequency nadir because there's no megawatt. Normally, there's no megawatt coupled with it. The grid forming can inject a megawatt, so which really help for our case when we look into the orders DER momentization. Yeah, right now we do not see significant voltage instability issue. So we see that for the transmission level, our current resource plans, the GFM resource should be sufficient. For now, under that resource plan, we do not need synchronous condenser for transmission level.
Well, I think that leads into a question of a similar vein. This is coming from Sam Joseph. So I believe that low short circuit capability is a danger in high IBR systems. Are you shoring up this potential weakness with synchronous condensers or something else? Or is this really not an issue for you? I think you might have just answered that, but maybe you just want to reiterate what you were saying there. Or perhaps also there's a follow-on, perhaps improve protection capabilities.
Yeah, that's a really good question. Condenser definitely can provide a much higher fault current contribution to the system for the protection. But normally when we're talking about using the IBR to displace machine, we're not talking about the 1 megawatt displace 1 megawatt due to the capacity factor issue. So we're talking about a few times of megawatt capacity in the IBR side to displace a machine. And meanwhile, in our system, we have 1.6 per unit overcurrent requirement for the grid forming best component. So we looked into the plan under the IGP regarding the grid forming resource procurement. And I believe the results show that under that plan, the fault current for the protection purpose will be maintained sufficient.
And also very related to that question is an earlier question from Mari, where she was asking about what that overload capability is, which we said was like 1.6, and how long does that, how many seconds does HECO require that from the inverter, grid forming inverters?
5 seconds.
5 seconds, and that's sufficient for the types of events where it's needed.
Yes. So yeah, we believe 5 seconds should be sufficient for transmission fault level event.
And a follow-on question to that from Ari is, do you have any similar requirements for your grid following inverter-based resources on the system?
No, right now. So we first of all, most of the time the current plans we do not procure grid following resource or grid following anymore, such as standalone solar. We do not procure that anymore. And for plant like PV and the best hybrid plant, and normally the PV for the AC coupled PV inverter will be the grid following, and we do not have short circuit current contribution requirement for that component. We only have requirement for the best component, best inverter component.
Makes sense. Thank you. So I have a question, is kind of bringing it up, it's a little bit to a higher level on all your planning processes that you went through and your generator interconnection studies. What's the general timelines of like, how often are you performing these? And like, do you think however often you are doing that, is that fast enough? Do some parts happen on different timelines than other parts? Yeah, if you could get into that, that'd be great.
So we've been doing we've been in this loop of a lot of procurements basically. So in the procurements, and because our systems are so tightly coupled, we do the group studies. So the group studies basically take I'm going to say around I think it was like 6 to 10 months of the actual study itself. But when you take into account the model checkout process, which is basically a feedback loop between us, our consultant, the OEM, their consultant, that's a kind of variable time frame. And so all that needs to be done before we can start the study, because it's a portfolio study. And what we've also seen is that sometimes as we do the portfolio study, projects drop out, and then we have to iterate, or we find one of the models, or there's some issue with the performance, we have to fix that and then restudy. So I would say like a 6 to 10 month study timeframe can turn into a 1.5 year timeframe with all the iterations involved and variables.
And how does that process of evaluating those new generators all together work within your integrated grid planning process?
Well, the integrated grid planning process is looking at what is the expected portfolio, And so within that, we do a group study, and that's much simpler because that's us making kind of or working with community, but coming up with a resource plan that is an assumption, right? And then we're doing the study on that. So that's much simpler than kind of working on a study that has that variability of things changing, things dropping out, things not working, and then we need somebody else to fix. Yeah.
Gotcha. And then one other question on the same topic of how often are those integrated grid planning reports done?
Okay, so the one that we just did was 2018 to 2024. That's the first one we've ever done. We're starting our second cycle this year. So that might be another, we're hoping to make it much shorter, in like I think it's like a 3 to 4 year time frame. But yeah.
Great. All right. Well, thank you both so much for your presentations and all the Q&A. I think we're going to start to wrap up. And I'm going to pass it over to Gwen in a minute here. So we've had a really information-packed morning. I hope everyone was able to take away a lesson learned, if not multiple. I know I sure have. And we greatly appreciate all the time of all our speakers coming from all across the country to be with us today. Now I'm going to turn it over to Gwen, who's going to close out this webinar. Thank you.
Thank you, Felicia. And thank you. There's a lot of really great information. There's lots to digest there. I'm actually looking forward to going back and listening in to some of that a second time once it's posted online. I particularly want to thank all the presenters, including Ken and Lee. I know all of them, both today and yesterday. They're very busy folks, and the time that they've taken to join us and share their knowledge has been really valuable and appreciated, and I think gives us a lot of food for thought. So anyhow, the recordings for the workshop will be available on the Alaska Sustainable Energy Conference website. So for those of you that are here, you found your way to that website. But please, continue to check back for more information on that, and also for the next workshop, which should be October 28th and 29th, as mentioned previously. We're going to be sending out a short survey following this workshop, and we would love to get your feedback on that. You can access it by scanning the QR code on the screen now with your smartphone, or we're also putting a link in the chat right now. It would really help us because we're still working on finalizing some of the future topics and things like that. We want to make these as useful to the audience as possible. So we will definitely be paying attention to those survey results. So it would be really wonderful if you can take the time to do that. And then finally, so we mentioned the next workshop is October 28th and 29th. And then as Andrew mentioned earlier, we have selected the dates for the next Sustainable Energy Conference at the Denina Center in Anchorage, May 19th to 21st. So tickets are going to be available at the Alaska Sustainable Energy website, and we hope that you will consider joining us. And I will actually put that invitation out to our invited speakers as well. It would be wonderful if you have the time or capacity to come and visit us here in Alaska. It's a really great networking event. So anyhow, with that being said, I would like to thank all of you for joining us for the Lessons in Transmission Planning virtual workshop, and have a great afternoon or evening, depending on where you're located. So thank you.